Good day, everyone, and Assalamu alaikum. On behalf of Global CIO Forum, Atos, and AMD, I welcome all the online attendees to this live virtual summit titled Advances in High Performance Computing, Tackling the World's Largest Problems. In this live virtual summit, we will understand how advances in high performance computing can help to tackle the world's biggest problems, whether it is weather forecasts, cleaner aircraft engines, genomics for personalized medicine. All these use cases require the computing power of supercomputers. Atos is developing today innovative, high-performance computing systems to solve major challenges of the 21st century. And Atos completes the entire HPC stack for its channel partners. Leading us through this live virtual summit are Andy Grant, Global VP, Strategic HPC Projects at Atos, Michael Clem, Principal Member of Technical Staff and Senior Field Application Engineer AMD. And now, before I hand over to Andy Grant, here are some short housekeeping rules. All attendees are on mute throughout the session. However, we encourage attendees to ask questions through the chat option, and the speakers shall answer them at the end of the session. So I'd now like to welcome Andy to begin this live virtual summit. Welcome, Andy.
Thank you very much, Aaron. So, in 1 second, I shall just share my screen. So, can you confirm that you can see my screen and it's in presentation mode?
Yes, I can see the slides, Andy.
Okay, great, thank you. Okay, well, thanks everybody for attending. As Aaron mentioned, I'm responsible for strategic HPC projects within Atos, and I will be talking you through, spending the next 20 minutes talking through some examples of work that are happening with our customers in some vital areas of science. But I'm going to start by giving a brief introduction to high performance computing and to Atos, and where Atos sits in the high performance computing world, and also Atos internationally for those who don't know the company too well and the technology too well. So first of all, high performance computing, what is it? Well, often called supercomputing, it's the use of extreme computing power to model and simulate complex phenomena. So that could be stress analysis on cars or airplanes, it could be modeling interactions of DNA, climate modeling, energy, and so on. Basically, used for design of products, financial modeling, physical simulations, and also it's an underpinning technology for AI and machine learning. A lot of AI algorithms sit on top of HPC platforms. Now, it's used across pretty much all industries where there's a need to address bigger problems with higher accuracy or greater speed. I often summarize HPC by saying bigger, better, faster, or the tagline that we've adopted more recently is faster, smarter, greener. Essentially, aiming for the ability to tackle bigger problems in a fixed amount of time, or the same size problems in a reduced amount of time, but also challenges of doing it more efficiently, and both in terms of time and energy, and in a more intelligent, smarter way. Now, as well as the requirements of industry, it's fundamental for governments as well, not only for things like defense mapping, securing energy resources, and obviously the global grand challenges of climate change and Earth systems modeling, but also, as we've seen very much over the last couple of years, the control and management of epidemics and pandemics. Without HPC, it wouldn't have been possible to sequence the DNA of the coronavirus as quickly as happened, and it wouldn't have been possible to develop the vaccines and the antiviral drugs that are now emerging to help with the stemming of the virus. All of these things are fundamental. One of the critical things, though, is about keeping ahead of the race, if you like, being able to predict ahead of time what is going to happen, whether that's climate change or financial markets. The ability to use advanced computing to predict ahead of time is often, you know, a fundamental aspect of why people or companies and governments adopt HPC. So what is Atos's vision in HPC? Well, principally to design innovative, efficient hardware platforms, both on-premise and cloud-based, to enable our customers to achieve the breakthrough science and the business benefits that they need. And that's in high-performance computing itself, in developing AI platforms and scalable AI platforms so you can tackle, you know, the bigger machine learning problems, and also quantum computing to provide a great way to quantum computing for the next generation of advanced computing technologies. And we want to do this in a very sustainable way. Atos as a company has committed to reaching net zero and our own decarbonisation efforts by 2028. That's a very ambitious goal, and HPC is fundamental to that, because the ability to drive, to develop platforms that are energy efficient is going to be critical to not only our efforts, but also those of our customers and partners as well. In terms of, you know, where Atos sits around the world, we're a large organization. We have around 110,000 employees globally. We're headquartered in Europe. The company group is headquartered in France, and that's traditionally been our kind of main focus. But we expanded and we're now working in 73 different countries. We're about a $11 to $12 billion organization globally. Specifically in the Middle East and Africa, we have around 4,000 technologists in 40 different countries, 20 offices in the region, and various delivery centers as well. So we have a strong presence in the region, although it is true to say that we don't particularly have a strong presence in HPC in the region, particularly in the Middle East region. Hence, you know, this seminar, where we want to, you know, identify, encourage, and build new partnerships in the region to help us in our efforts to expand using our unique technology combinations in the Middle East region. In the world of HPC, AI and quantum, we are the #1 player in Europe. We deliver to pretty much all of the major research centers, both academic centers, government research labs, and indeed, you know, defense research labs as well. And expanding out of our footprint in Europe, we are a dominant player in South America now. We have footprints in North America, and as I just mentioned, you know, we want to grow our footprint in the Middle East and are looking for the right partners to work with to enable us to do that. In addition to those traditional research labs and research-driven organizations, Atos has many industrial partners and industrial customers as well. You can see there many logos for, you know, key automotive manufacturers, large-scale weather centers, energy companies, pharmaceuticals companies, who are all using our HPC technology to develop their own products, many of which I'm sure, you know, people on this call will drive those cars or use those products and services. So indirectly benefiting or influencing, you know, the day-to-day activities of many people on the call. Now, the aim of today's webinar is not so much to talk to you about the products and services that we have, that can come later, but really to talk about some of the advanced research that's happening with some of our customers and the impacts of that, and why we feel it's critical and that HPC and supercomputing are such fundamental technologies for for governments, for industry, and for other organizations. So weather and climate modeling. So obviously this is impacting us all. There is no doubt now at all. I think about the climate is changing, the climate is warming, and that there are extreme weather events happening all the time. Just in the last year, there's been, I think, over 1.3 million fatalities around the world as a consequence of extreme weather events, and trillions of dollars of economic damage. Being able to understand and predict ahead of time when these extreme weather events are going to happen is critical, whether it's rising temperatures, which is the top video here, rising sea level and ice changes, which is the video at the bottom here. Now, climate and weather have always been large users of supercomputing. There is a need to examine these phenomena at much higher levels of detail than is currently happening today. This picture on the right-hand side is showing changes over the last 30 or 40 years on the resolution of weather and climate models. So you only need to go back about 30, 40 years, and the grid spacing, the spatial resolution of the weather models was about 500 kilometers. Because of the advances in supercomputing, we're now down to about 2.5 kilometers for very specific events or areas. So you couldn't model the whole globe very easily at 2.5 kilometers, but you might be able to monitor the weather and climate in specific areas, perhaps over an event such as the Olympics or something like that. But 2.5 kilometers is not good enough. It's not good enough to examine the fine level interactions in the detail that's needed to really understand the impacts of climate change. The models need to change and adapt. So we're involved in a project called EasyWays, which is around developing next generation weather and climate models using targeted at exascale supercomputers. It's with leading research labs, weather labs around the world. And the idea is that within this project, we'll be able to take those spatial resolutions down to under 1 kilometer. And that's critical to modeling low-level cloud interactions. So to be able to model clouds and precipitation at a very fine detail is critical to understanding how heat is trapped within those layers, which is critical to understanding how much is released into the environment and trapped as carbon in the atmosphere. So all of that, though, requires additional driving of the resolution of the models, additional complexity in the models, and probably additional ways of running the models as well, multiple ensembles, all of which significantly drives the computing resources required to do that. Hence, the push for exascale 10 to the 18 size systems, computations per second size systems that are happening around the world at the moment to try and create the capability so that more complex models that are at a kilometer or below resolution could be run to understand those fine level interactions. Critical that we do that before the world heats up too much to be able to understand actually what's happening. One possible way of reducing the time to do that and getting ahead of the game is by using AI or machine learning as part of weather and climate modeling. So this is some work that we're doing with ECMWF, the European Centre for Medium Range Weather Forecasts, and it's looking at, can parts of the weather forecast model be replaced by deep learning neural network models? So the two pictures here, one is using a conventional forecast system and one is using an AI system. At first view, they look identical. You couldn't really spot the distance at this level of granularity. However, there are differences, and as you drilled into the detail, you would see those differences. But at a first level, it looks like the models are working well, the dynamics are working well, and the forecast errors are comparable. However, what's lost is a little bit of the understanding of the underlying physics and how to increase the complexity and fix the different feature interactions at a higher resolution. So this is an area where there's a lot of promise, a lot of research activity to look at how AI models could be used in forecast systems, but it's not there yet. But certainly an active area, and this is a part of a whole area of where AI and HPC are converging to some extent. The next project is kind of related in a way, and this is around Earth systems modeling, solid Earth modeling, which effectively means earthquakes, volcanoes, tsunamis. In a similar way to the weather forecast case, the ability to understand the dynamics of, say, volcanic ash clouds moving over space is critical. So building high resolution models for those is also vitally important. Similarly, for tsunamis, understanding the height of the tsunami wave, when it's going to hit land, and so on, is critical to evacuating towns and cities, to save lives and to minimize damage. This project, Cheese, again with major research labs, is looking at how you could build more accurate models to model these phenomena and at larger scale, but also look at how you can couple different models together. So for example, in this image that's on the screen at the moment, we've seen there's been an earthquake in Chile that is creating a tsunami that at some point is going to hit Australia, New Zealand, and so on. So this is two different types of model, the earthquake modeling and then the impact on the tsunami. Looking at how to couple those models is an extremely challenging problem that's taking the best minds on the planet to look at those. And then doing that at extreme scale to get the fine resolution is, it's at the forefront of science today. So those are some examples of what we're doing in public sector research. Moving into a completely different area and into energy, the energy sector, a project that we've been working on with Total is looking at how they could, it's a carbon sequestration problem. So simulating complex molecules that can capture and trap carbon. And these molecules that the modeling are very large in size and difficult to do using traditional HPC technology. So they're looking at how they can use quantum computing technology, so next generation, if you like, to look at these complex interactions and to model and simulate the properties of these molecules. And then in particular, they're looking at a class of molecule called metal organic frameworks. And the idea is that the yellow sphere in this molecule is the MOF structure, and that's the principal actor in the CO2 capture. So these molecules interact with the CO2 in the atmosphere, trapping it into the core of this molecule. So this is very promising work. It's complex work because the size of the molecules and the interactions are so large, but obviously very, very interesting and could yield some vital results in the future. Moving on again in this case, we're looking at a life sciences problem here, and a lot of what I've been talking around is really around developing digital twins. So it could be digital twins of an Earth system or a weather forecast model or a manufacturing problem. In this case, the digital twin is a virtual human. This project, which is called CompBiomed, we're involved along with a number of leading research labs again, is looking at developing a digital twin of a human. This particular model that I'm showing here is a virtual model of a heart. And the idea is that you create this virtual model using MRI scans and blood flow data and other forms of data, CT scans, etc., from an individual. You create this virtual twin of that individual, and then you look at, say, the blood flow properties, which is what we're seeing at the moment, through that virtual heart. Then the idea is that you would test drugs virtually using this digital twin before you test them on the individual. And this is yielding very high promise. It's showing that these interactions with virtual heart models are more accurate than trying to model what's happening using animal models, animal hearts, or animals to test these drugs. Now, if you think that the time between, say, the initial coronavirus vaccines being developed, which was effectively at the start of last year, to the time when they've been distributed and available, to populations around the world, the bulk of that time has been around testing the efficacy of those drugs. Now, obviously, nobody really wants to rush that process and develop drugs that are going to have an inverse impact. But if you could speed up that process by using virtual models, you could see a scenario where in a few years' time, when the next pandemic happens and the next antiviral drugs need to be developed, you could test them first on the virtual models and get them to market much quicker. Completely different industry again. In this case, manufacturing. Atos has many manufacturing customers, and a lot of car manufacturers are using our supercomputers and our consultancy services to model their cars and stress analysis and things like that. In this particular case, I'm looking at an auto manufacturer, a German auto manufacturer, who's using advanced simulation for product development, manufacturing, fuel economy type developments, and also looking at stress analysis in virtual crash simulations. And the idea is that you would create optimal designs early on by testing virtually, reducing late design changes, and then you're increasing your product effectiveness. Now, in this particular case, the customer is reporting that to do a physical crash test of a car with cameras and sensors and so on, it costs about $500 million. To do a virtual test costs around $100, and you can do it as many times as you want. So the ability to fine-tune your design virtually has massive benefits. You can translate that, not just from the automotive sector, but to the aero sector as well, similar kinds of problems. A different manufacturing case study here, and this one is an AI issue, and this was an aircraft manufacturer that we work with, where they had the challenge of trying to spot anomalies deep inside aircraft wings. And these anomalies would be things like foreign objects that have not been removed, sealants, bolts that are in the wrong position or have been dropped, and so on, that cause damage later on. So the idea was to cut 1 to 2 days off their 30-day assembly program and aid in the QA inspection. So we developed AI models to do this by inserting cameras, building up image banks, training models to do this, so that these things could be spotted virtually rather than having somebody have to do physical inspections. And that, of course, yes, it's an AI model. It's running on a supercomputer to enable that to happen. Similarly, this same technique could be applied in many different areas of manufacturing where there's inspection type problems. The final case study that I'm going to look at is in financial services. There are many areas where HPC and AI apply in financial services through frequency trading, but typically a large case, and particularly at the moment, is around fraud detection and credit card fraud detection. One particular customer that we're working with, a global credit card company that's handling very large volumes of transactions per year, and has seen a spike in transactions because of online trading over the last year in particular. They're using AI and neural network techniques on an AI supercomputer to wade through these volumes of data, trying to spot anomalies in the transactions and pick out fraud activity much sooner. They've managed to do that and make significant savings, and then are looking at how the AI solutions can be applied onto different areas of their business, different areas of financial services. So large number of application areas. So hopefully that's given you a feel of some of the areas that Atos is working in across different industry sectors and the global nature of some of those problems. I just want to end by, this wasn't intended to be a product pitch in any sense, and hopefully I haven't done that, but just to show you a picture of the end-to-end solutions that Atos has. So starting from quantum machines at one end to supercomputers, AI at scale, and then high-end data analytics systems and mid-range HPC systems, and a full software stack to go along with that, including hybrid cloud technologies and so on. We also do modular data centers, so we frequently build specific data centers for customers. Atos is a full end-to-end systems integrator, so we manage the delivery, we manage the support, professional services, consultancy services around that, which means that partners that we work with, we can provide you with a complete package, if you like, dependent on the level of interaction that we need to enable you to have the feet on the street, go and interact with the customers locally, and then we can help do the rest. Okay, I'm now going to hand over to Michael from AMD, who is going to talk to you specifically about some of the newer AMD products, and then I'll come back shortly to talk about some of the joint work that we're doing with AMD. So Michael, over to you, and then we'll come back at the end for questions, if that's all right.
Thank you. All right, so my slides should be coming up now. All right,
yes,
there they are.
Yeah, go
Hello,
ahead.
everyone. So I'm Michael Clem. I'm a principal member of technical staff at the HPC Center of Excellence at AMD, and I wanted to talk about how we at AMD help solve the complex challenges in HPC that Andy was talking about. And since I'm coming from a hardware company, my presentation is slightly geared towards providing you with the hardware and also a tiny bit of a software perspective on the products that AMD has that help you solve your HPC challenges. Let me show the legal disclaimer for a second. Standard legal stuff that I have to show with every presentation. Now, the important people that take good care of our customers in the Middle East area are shown on that slide. So there's Saeed, who's a senior account manager. There's Mohammed, who's a field application engineer, so a technical colleague of mine. And then obviously there's me, who is also working on technical questions in the HPC Center of Excellence. So feel free to reach out to any one of us three if you have follow-up questions or if you want a deeper dive on any of our products and technologies. All right, in terms of the agenda, what I want to run through real quick. So I'm going to talk a little bit about EPYC processors, which is our main workhorse, not only for HPC, but for computing in general. Then I'm going to talk a bit about Instinct accelerators, which is our GPU line of compute hardware. And then I'm going to close the presentation with a tiny glimpse at our software stack that helps you actually run software on our hardware. You've seen many of the HPC challenges already. Here's just 3 of them, not as nicely animated as Andy's slides though. So I picked like 3 different scenarios here. So there's the left one, that's a galaxy simulation where people want to understand the fundamental workings of all of the universe, and how the filaments, the voids, and in the galaxies emerged from the time of the Big Bang, to explain how our universe became into existence and how it formed together understanding of how everything works. In the middle, there's something similar that you've already seen before. So this is an earthquake simulation, trying to understand how the waves of the earthquake propagate through the crust of the earth. And again, the idea here is to predict where damage might occur and to provide safety for people, and potentially also, factor these decisions into where to build buildings and how to build them. And then on the right side, there's a picture of a quantum chromodynamics application. These are applications that try to understand the fundamentals of matter and how atoms and matter forms and what property it has. And so, it's kind of tightly connected also how the universe became into existence, so that mankind gets a better understanding of how things work and the physics behind them. All right, now let me talk about EPIC processors. So since a few years we have the Zen architecture out. Current iteration of that, or current generation of that, is codenamed Milan. We launched that product, I believe it was in March this year, and that's kind of the newest and fastest processor that we offer from AMD. Over the past years, going from the first generation Zen cores to the second generation Zen cores and now the third generation, we continuously innovated on the way the processor is built and the capability it has. So the idea here is that the processor gives you the flexibility, depending on the different natures and requirements of the applications that are running on these processors, that you get a flexible system that can easily adjust and adapt to the requirements of the applications. So some of the examples that Andy and I were talking about need a lot of memory bandwidth. So the processor needs to talk to the memory system of the cluster as quickly as possible. While others, like the quantum chromodynamics example, are more compute bound, so they have more numbers that they want to crunch in the processor cores, and so you need a flexible hardware architecture that kind of strives to easily adapt to both those requirements. We are right in the middle of preparing the next generation, so the fourth generation of the Zen cores. The code name is Genoa. It will be manufactured on the then at launch available manufacturing node. And obviously, we're going to improve and innovate in that product again to make sure that this is going to be the best possible platform for your HPC applications. Let me just quickly show you some specific features and call them out so that you can understand why we believe that EPIC is the best processor for HPC applications today. So I already kind of alluded to the enhanced memory performance. And so the way we interact with memory was fundamentally changed in the EPIC processor. It's a bit of a technicality, but pretty much there's an on-chip network that makes sure that all the cores and all the components of the processor can talk to each other. And then there's the external attachment of memory. And what we did is we synchronized those two networks, on-chip networks, so that now both the processor and the external memory is running at the same frequency, and that gives a great performance benefit for applications that are talking a lot to the memory. The other thing that we did is we increased or we changed the way the caches work on the system, and I have a specific picture about this on that slide. So what we did is we redesigned the way the processor is built up so that it becomes more flexible and more easily adjustable to the actual workload that you're running. So in the previous architecture, there was only a certain amount of cache that each of the cores was able to access. And if you had an application that was using less cores, you were limited by the amount of that cache that you could access. With Milan, we changed it such that this is now twice as big, so that you have more flexibility in how you assign the cores to the caches and how you lay out the application on the actual machine, so that the processor more easily adjusts to the requirements of the application. Right, let me talk about GPUs. So this slide shows you kind of a tiny peek at the history, just to show you how much innovation has happened in the past 2 decades. So if we go back to the year 2000, there was a supercomputer ASCII-White at one of the DOE labs in the US. That was the #1 supercomputer ranked by the top 500 list. So that's certain LINPACK benchmark that is used to rank those supercomputers. And that system was #1 in that year. It consumed 6 megawatts. It weighed 106 tons. And from the picture, you can see there was a fairly large machine. And that computer had a peak performance of 12.3 teraflops per second. So that is 12 trillion operations on floating point numbers. So, you know, decimal numbers per second. In 2020, so 20 years later, there's the AMD Instinct MI100 GPU, which has 300 watts, 1.1 kilos, and 11.5 teraflops peak. So if you correlate those numbers, within 20 years, AMD and the industry were able to squeeze the amount of compute performance that a supercomputer had in the year 2000 into a single GPU that is like, I actually did the math before the presentation started. So it's 90,000 times lighter than the original supercomputer. And the amount of power that it needs to provide that compute power is 20,000-fold lower than the ASCII-White supercomputer. So that's, you know, just a historic perspective on what has happened in the past 20 years to shrink and squeeze more and more compute power into a single system. All right, also kind of a bit of a history with an outlook to the future. So over the past, since 2000, the past 20 years since 2000, it became quite clear that the CPU-only terascale era may potentially not extend into the exascale area that we are pretty much at the dawn of. Right, so that is about 10 years ago when GPU accelerated petascale came into the game, where people found that it's more power efficient and a lot smarter to have heterogeneous systems that are comprised of CPUs plus accelerators, in this case GPUs, to increase the efficiency and the computational power of these systems in supercomputers. Now, for the exascale era, it became clear to us that standard GPU technology will not be the technology that will drive exascale in a sufficient manner so that it becomes as power efficient as possible and technically feasible. So that is now the blue part that starts with Frontier and El Capitan, which are the two exascale systems that have been awarded to AMD technology, and that will make use of the new generation of technology that is coming from AMD. And what I mean by that new technology is this. So if you think about the spectrum of things or applications or application domains that a particular hardware can support, in this case, a GPU, you know, for GPUs, graphics processing units, there is obviously something like real-time pixel rendering, you know, like actual graphics output for games, for media, and for other visualization purposes. And then on the other hand of the spectrum, there's compute intense workloads like, you know, HPC and machine learning and artificial intelligence. Now you can build a general purpose architecture that kind of serves both, right? But on both extremes, so when we go to the extreme computing case like exascalers, or when we go to the extremes graphics case, the hardware becomes less amenable and yes, less well adapted for these cases. But there's a good hump in the middle where you can think of that it's in general supporting you know, a vast majority of applications. Now what you can do is though, you can specialize the hardware, right? You can produce graphics cards which are actually optimized for the initial purpose of GPUs, so graphics processing, and you can specialize them into compute optimized architectures that are GPUs or compute accelerators that are really geared towards number crunching and HPC workloads. And this is what we did at AMD with the MI100, and what we will do going forward with the future products as well. So this is now called CNDA architecture. And what we did is we basically took a regular GPU, we ripped out everything that is graphics related, and increased the compute capabilities with the real estate and the silicon in the processor that we gained by removing the graphics parts to a large extent. And with that, we get a much better performance behavior of the GPU for compute-driven workloads. All right, so we are now right in the middle of this slide with a product called Instinct MI100. That's as I said, the first instance of the CNDA architecture. So where we have made that split of the compute architecture to be its own compute architecture. That's the second generation, and that is our HPC workhorse that is optimized for HPC applications and machine learning, as well as HPC. We do have a future roadmap for these products. So there's CNDA2, so a third generation of this Infinity architecture that is then going to be the basis of the exascale systems that are coming in the next years. Again, this will be manufactured on the by then available manufacturing node of our foundry. All right. Now, as part of the node level design, the way this works is that, you know, there's the EPIC processor as the host system, and then the GPUs attached to this host processor using standard PCI Express links. And within and across the GPUs, there's a special AMD Infinity Fabric technology link that allows each GPU in a group of 4 to talk to other GPUs in that same group with low latency and high bandwidth interconnects. Right, and you can have in a dual processor configuration, you can have 2 of those hives, or you can decide for a single processor configuration where you would have just a single hive of these GPUs. All right, and then, you know, the architecture. So this is, as I said, is really made for performance. And even though you'll find the word shader engine on this slide, it's kind of a misnomer in the architectural diagram. There is no texture processing on that thing anymore, right? It's all full of compute units. There's a large L2 cache so that you can keep data close to the compute units. And then there is on the left-hand side and the right-hand side, there's the ports to attach high bandwidth memory so that you get a nice 1.1 terabytes per second memory bandwidth from the GPU memory to the GPU's compute unit. The important thing to highlight is, as I already said, it's geared towards HPC and machine learning and AI. So, there's this architecture supports the usual suspects of data types. So there's FP32 and FP64, which are more HPC kind of data types. And then there's int8, FP16, and the BrainFloat 16 data types, which are more amenable for workloads that are coming from the area of machine learning and artificial intelligence. All right, now finally the software stack, right? So no hardware without software. So what we do have right now is we have two product lines of software stacks. One is for the EPIC processor. The other one is called Wrapup. That's the Radeon Open Compute Platform. That is the software stack that is geared towards running software on the Instinct accelerators. And let me give you some details about those. So most of what we do is based on open source. So we do absolutely support the traditional platform compilers, so either LLVM or GCC. These open source versions have all optimizers that understand the specifics of the EPIC processor and can compile code, efficient code for the EPIC processor. We also do have our AMD compilers, so the AMD Optimizing CPU compilers, or AOCC for short. That is pretty much an LLVM compiler that has some additional secret sauce in the compiler so that it provides more efficient code and contains some core IP of AMD to produce even better code than LLVM can do. Then there is the AMD Optimizing CPU libraries, or AOCL for short. These are our math libraries. So these are libraries that support mathematical operations like matrix multiplies, fast Fourier transformations, and these kind of standard operations that you see in almost all HPC applications. Then there is SenDNN. That's a neural network library for inference acceleration on the CPU. And then there's MicroProf. That's our performance and profiling tool so that you can gain insight into the behavior of the application on the EPIC processor in case you need to understand if there's a performance problem or if the code is running as fast as it can. All right, and then as for the GPU, so in 2021, we released Wrapup 4.0. By now we're at 4.2, so we cranked up the patch levels already. When you look at the blue rectangles, what the software stack supports, you'll see all the open standards that are relevant in the HPC industry and also beyond the HPC industry. So there's OpenMP, the de facto standard for shared memory, parallelism, and heterogeneous programming. There's OpenCL, there's MPI, which is another standard programming model for distributed systems like clusters. There are all the BLAST libraries that we need. There's also machine learning and artificial intelligence libraries and frameworks that we support. We are fully integrated into the Slurm job manager that is typically run on larger clusters to give users access to a particular subset of the system. And then there's Docker, Kubernetes, and Singularity, and the container-based execution frameworks so that you can actually download an application container and just have a ready-made, ready-to-run solution that you can run out of the box on your system. All right. Let me summarize. So, hopefully you took away that EPIC processors really drive application performance via the architectural innovation that AMD did in the past 10 years. So we greatly improved compute performance. We have an outstanding memory performance, I didn't speak too much about I/O performance, but there's also a quite capable I/O system attached to the EPIC processor so that you can efficiently talk to the fabric of the cluster and or an I/O subsystem like SSDs. Then we talked about the AMD Instinct accelerators, which is this high-performance GPU architecture specialized for and designed for HPC, AI, and machine learning. And it was the first GPU to actually hit the 10 teraflop mark in 64-bit double precision performance. And then there's the AMD software stack that I briefly talked about that supports an open and productive and programming environment for said hardware, so for the EPIC processors and the Instinct GPUs. And that's all I had to say. Thank you for listening. So back to you, Andy, I guess.
Yep, thank you, Michael. So next we want to go through some kind of joint examples of Atos and AMD working together. So if you could make me presenter again, I shall share my screen. Okay. Can you confirm that you're seeing my screen in presentation mode? I'm sharing the right screen.
Yes, Andy, your screen is visible, slides are visible.
Okay, great, thank you. I wasn't sure whether I was sharing the right view. Okay, so yeah, in this next section, just before we come to Q&A, we want to just go through some real-world examples of Atos and AMD working together in HPC, and so I'll cover a few, and Michael will cover a few as well. But just before we go there, I should have mentioned previously my colleague Kaya, who's on the call, another panelist in this session who will probably join us for the Q&A session as well. Kaya is our main person, manager of the HPC and big data and cyber business in the Middle East. So as well as myself, use Kaya as the main point of contact for Atos in the region in regard to HPC products and services. So Atos and AMD, as we've had a very successful partnership over the last few years, going back through several generations of EPIC processors. So, you know, from the first generation that Michael just described to the product developments happening now on the latest generation. A good example of that is the Rome processor, which was introduced in middle of 2019. Atos was the first vendor globally to bring that product to market, and also, you know, had the world record for the benchmarks on that system, because of our innovative direct liquid cooled design, we were able to squeeze a little bit extra performance out of the processor than some of the other vendors. So we had the world record for running AMD processors in our systems at that time. Just over the last few months, we shipped our 100,000th AMD EPIC processor. That was a major milestone for us, for the relationship. And in fact, just in the last few months, in the new top 500 list, we've had new entries, you know, representing around 25,000 new processors from AMD. Most of these are Rome processors, and we're starting to see, you know, some of the newer generation Milan processors now be deployed in practice. A good example of that is this system, which is the Joule system in Jülich in Germany. This is the top system in Europe today, and it's a converged HPC and AI platform used for a lot of the projects actually that I mentioned in the previous section of the talk. So a lot of the work that I showed has been run on this platform. And that, I believe, was one of the first systems jointly developed or brought to market by Atos and AMD. But there are many others. These aren't the same size, but we'll see lots of deployments across different countries, mainly in research labs, where we've got joint deployments using AMD processors in our Bull-Sequana platform, which is our advanced HPC platform. The commitment is beyond just using AMD processors. Clearly being first to market, early integrations, strong commitments, working together to productize. It's not just a plug and play, away you go kind of relationship. There's a lot of joint development goes on between the organizations to make these things work together nicely and get that extreme performance. I mentioned ECMWF in my previous talk. So this is the European Medium Range Weather Forecast Center. Probably our largest AMD deployment to date is happening with ECMWF. The system is in the final stages of acceptance today, finally being completed. It has around just shy of 8,000 AMD nodes, a million cores in this system, representing about 37 petaflops of performance. It's the world's largest production weather supercomputer, and a lot of the projects that I mentioned, easy ways, the climate modeling activities, will be happening on this machine. It's basically there to enable advanced weather forecasting and monitoring of severe weather events to provide advanced warning so that remedial action can be taken. So literally, these systems will be part of early warning systems that will inevitably save lives. Atos and AMD done extremely well in the weather market globally. These are just some of the wins we've had over the last few years, the joint wins. From the German Climate Research Center, Météo France have renewed, DKRZ have renewed recently, Dutch, Spanish, Croatia is DHMZ, and so on. So strong contribution, strong presence in this market, and that is not just because of the technology, but because of the engagement we make with these customers to get involved in the research activities and provide our applications expertise and performance expertise in projects such as the ones I mentioned previously. It's not just selling technology for technology's sake, but engaging with that community to really understand and drive the science forward. Michael, over to you for the next one.
Yes, thank you. So here you can you please go back to Andy sharing the screen?
I'm sharing the screen, yeah. Oh, okay.
No, somebody took away the screen sharing from you.
That's a wrong presentation. Okay, you see that now?
All right, thank you. Thank you. Sorry about that. All right, so just some real world results with AMD. So these are like 5 proof points that I picked from the domain of automotive. If you are interested in other domains, there are other proof points that you can click through. I'll come to that in a minute. So whether it's crash simulations, fluid dynamics, finite element analysis, or as Andy was alluding to, weather forecasting, we have application proof points and application recipes that are ready made for you, so that if you don't know how to run a specific applications, there's a good chance that we have a recipe for you that you can implement and then use that recipe to run the application on your system. Andy, please advance to the next slide. So here's, this is the database I just mentioned. So if you go to amd.com, processor, server technology, server tech docs, and white papers, you can, browse through the whole set of proof points that we have created. And many of those proof points have the mentioned ready-made the ready-made recipe how to build and run the application for the best possible result on our system. We also do offer spec recipes for open source software. So if you have the spec package manager installed on your systems, you can use that to run and build and run applications with the tool chain from AMD and supply the right side kind of options to those tool chains so that you get the best possible result. We also do have the AMD Infinity Hub. That is a repository of Docker containers that contain ready-to-run applications, like for instance GROMACS, one of the molecular dynamics simulations, has a ready-made container. You can just use Docker to pull that container and then run it on your EPIC system and or your AMD Instinct GPU partition of your system. Next slide, please. If you are unsure about what is the right CPU for you for your application needs, we have recently implemented a tool that tries to recommend particular EPIC processor SKUs, so models, and makes recommendations in terms of, if you have a certain application behavior, what would be the right EPIC processor for that. And obviously you can also, of course, talk to your Atos representative who will have access to the same information and can also make a recommendation. But we do offer that tool as part of our website for you to, make a first check on what could be the right processor for your needs. Next slide, please. And then finally, if you are more interested in GPUs, there's the Instinct Education and Research Initiative. The basic idea here is that we appreciate that not everybody already has access to AMD GPUs. And so you can register for this initiative. It's actually free of charge. And you can get access to hackathons, training tutorials, resources, supplemented documentation. You get access to a whole set of community and software packages. And you can also get access to the AMD GPU itself so that you can start working with it, develop your code, validate the code, certify the code, or just run benchmarks to understand the performance behavior of the GPU better. If you're interested in, at the bottom of the slide, there's the links, amd.com/AIER. All right, next slide, please. So one thing that I wanted to close with is the question, or an answer to the question, how do I bring existing GPU code over to an AMD GPU? So if you already have applications that are GPU enabled and that use the CUDA model of things, there's actually a porting tool that we offer. It's called Hippify. The process then is called hippification. And so here are the three applications that I was showing earlier. So the galaxy simulation, the earthquake modeling, and the quantum chromodynamics simulation. And down there, I give a rough overview of how long it took us to port the existing CUDA code of that application over to run on the AMD GPUs. So for the Galaxy simulation, it was actually done in an afternoon. The tool did all of the heavy lifting to translate the CUDA code into, in this case, HIP code for AMD GPUs. And then it took us a few hours to make sure that the build system of the application understands the new code. SpecFilm 3D, a lot larger than the first application. That was ported in a day, similar idea. The tool brought us like 90% of the way, and the last 10% was making sure that the build system and the environment of the application actually picks up the ported code. And then there's CUDA, which is this library underneath that chromodynamics library application. And that was ported in 3 weeks, and that might sound extensive. And there are two reasons why that was extensive. Because first of all, CUDA is a highly complicated code. So it was a lot of translation that had to be made. But the more problematic thing with CUDA was, in terms of the porting, that CUDA was written against NVIDIA GPUs using low-level primitives that we do not support, because obviously we don't use NVIDIA GPUs and GPU processors in our products. And so these low-level things had to be translated by hand, and that consumed a bulk of the time. But the high-level code was translated also in like a very short period. All right, that's all I had to say about the software environment. Back to you, Andy.
Okay, thanks very much, Michael. I think that was the last slide. So Aaron, back to you for the Q&A session.
Thank you very much, Michael, and thank you very much, Andy. Absolutely brilliant presentations over there. So much information. Can I invite Kier also to join in the Q&A? Of course, Michael and Andy on standby. And coming back to the sessions, I mean, great takeaways from Andy's thing about the extreme weather modeling. We used to hear a lot about standard weather modeling in the 90s, and now, of course, the extreme weather modeling required due to the huge financial and human toll that it's taking. Great stuff from Michael on how the processors are moving between real-time pixel rendering and compute on the other side. AMD is supporting all the open standards for its HPC. Great comparison of power consumption in the last 20 years and so many other things. So if everybody is ready, let me just quickly look at the questions. Now, Andy, you mentioned something about Atos being the number one player in HPC and quantum in Europe. We have a question here. Probably KUR can also support this. How does Atos look at selling its HPC solutions in the region, distributors? Any update on the channel strategy? Go ahead.
Sure. Yeah, I'll start and then I'll hand over to you, KO, if that's all right. So that comment about the leading supplier in Europe, if you look at, say, the recent top 500 and look at the number of petaflops that Atos supply compared to other competitors, we're about double the nearest competitor in terms of deployed computing power. And that's not just because we have a large number of systems, but basically because of the power of those systems, we're addressing the top end supercomputer end of the market. Now, Atos has been growing 20% year on year in the HPC space, and our intention is to expand out of our comfort zone, our area around Europe, to make sure that we're addressing the broader market. And the key market that we're focused on over the next few years is the Middle East, and expanding our presence there. So you will see us expanding our own staff footprint there with additional specialists in HPC, big data, AI, but also developing channel partners and distribution partners in the region. Keo, do you want to say a bit more about the approach there?
Yes, thank you very much, Andy. So yes, from the Middle East perspective, Atos has been in the region for more than 10 years now. We have offices in UAE, Saudi, Qatar, Egypt, and in Turkey as well. Now, we intend to get very aggressive when it comes to specific HPC, business domain. In the next coming weeks, we have dedicated hires in terms of sales and technical sales in the region, focused exclusively on HPC. the intent is to be competitive, to gain as much market share as possible. And in that sense, we have decided not to follow a two-tier model, which means we will be selling directly into the channel. There will not be a distribution in between. As Andy had mentioned, that we support an end-to-end solution, which means for the channel, we bring on the table not just compute hardware, we bring the software, we bring the compute, networks, storage. In fact, we deliver the entire thing, including a rack, to the partner. So for a partner, it pretty much becomes a whole package rather than going to different separate vendors, separate support, separate SLAs. So with this USP, the intent is to sell directly to the channel, develop a channel ecosystem, a dedicated channel ecosystem, and grow the channel business in the region. So that's going to be our #1 priority in the next coming months and quarters.
Thank you, Keyur, and thank you, Andy. Similar redirect question coming that there are Atos components and the non-Atos components in any HPC solution. How would Atos approach it? Would you integrate and sell out to the channel? Any thoughts on that, Keyur and Andy and Michael? Go ahead.
Yeah, I mean, principally, we are a systems integrator. So we build our own systems, obviously, and we use components such as the processors from AMD, memory from the memory suppliers, and so on. They're integrated into our systems, but occasionally we will need to introduce third-party components, different storage products, different networking, and so on to complete the solution. Absolutely, we do that. Our architects are skilled at designing around the customer requirements to bring in those extra components as needed and provide the services and support around those. So we work with those other suppliers, IBM, DDN for storage, NetApp, and so on and so forth, to make sure we can provide the complete package and integrated solution. But typically, Atos will take responsibility for support and managing the background support arrangements with those third parties. So from an end user customer perspective, there's only one phone number to ring. You don't have to deal with those companies. We do that for you in the background, and our ticketing systems and support arrangements manage all that for you.
Fantastic, very interesting. Keyur, just to complete that, this support would be extended across Middle East in the initial stages, or does it go Middle East, Africa, or GCC? Go ahead.
This will be extended throughout the region. So as Andy mentioned, that yes, the HPC, HPC is a solution; it is not a product. So it will have multiple components, expanding beyond Atos, branded components. So for example, an HPC deployment might have 80% of DDN storage and 20% of NetApp storage with an IBM file system and so forth. So what Atos brings on the table is a complete package, a complete integration with a single point of contact and support for the channel, which is Atos. It's a single number. We again have different tiers of support: gold, silver, bronze, which are carved out based on the region's requirement. So the partner and the customer will only have a single window to manage to the SLA of all of these components.
Thank you, Keyur. Michael, just to get you to jump in, you mentioned about sizing of the HPC in terms of which AMD processor. Any thoughts on the type of application workload? We're seeing a lot of use cases presented by Andy, but if I was to just ask you for a thumbs up on how the roadmap works with applications, anything which you can give us over there, Michael?
Well, the only thing that I can pretty much repeat what I already said during the presentation is that we designed EPIC to be as flexible as we could make it, right? So that it absolutely supports the whole range of HPC applications, ranging from IO sensitive over to compute sensitive and memory sensitive. When you look at the SKU configurator or recommender, you will see that we do have different lineups of processors that try to target a specific subset of the sensitivity question. So for instance, we do have options where the processor layout is made so that we have the full number of what we call compute dies, so cores plus cache, but have reduced the number of cores per die. But we also have versions where we reduce the number of dies so that you get more processors per cache or more cores per cache. So, you know, the skewing and the way we cut the models tries to also adjust as much as possible to the application domain. So if there's a specific subset of application that the user is targeting, they can decide to go with the specific SKU that is targeting that domain, or you know, the higher bin models, they kind of automatically expose the flexibility, because the way you lay out the application on the system then can make a decision whether you want to pack it closely so that it uses most of the on-site or on-chip capabilities, or if you want to spread out the application somewhat more so that you can aggregate the capabilities of the system and the available processors.
Yeah, interesting. I think you mentioned at the beginning, it's the memory intensive, performance intensive, and IO intensive approach on the application workload, and I guess that's how AMD has mapped it out. And of course, it was well equipped to manage any type of configurations based on the workloads. Am I right, Andy?
Yeah, I mean, yeah, just picking up on some aspects of Michael's answer. One of the things that's becoming more and more apparent across all of the different application domains is how AI is starting to influence HPC in multiple ways. Not just the fact that HPC platforms underpin a lot of AI systems, but how AI algorithms are being introduced in core parts of HPC application problems. I use the example of the climate modeling one, but I could have used manufacturing examples. And I think you will see in next generations of processors a closer coupling of AI capabilities with traditional CPU capabilities to make that whole process easier from a programmer perspective. So,
very interesting there. Yeah, sorry, go ahead, please.
No, that was the point really, that closer interaction between the two technologies is not just represented in the software stacks, but also starting to be represented in the next generation of hardware developments as well. And,
yes, very interesting.
From a system perspective, you will see probably modular components. So you may see in an integrated system, part of a system that is looking just for CPU elements of a problem, another that's just looking at AI, another that's looking at quantum or homomorphic computing, and so on. And this provides an integrated platform where there's a high-speed interconnect connecting those different components, so that because for a lot of these application domains, there isn't a one-size-fits-all kind of approach. There are different parts that are suited to different types of architectures, and as kind of new types of applications emerge to take advantage of these architectures, we'll see a convergence of those things.
Sure, great. So what I was just saying was that obviously in the Middle East, the usage of algorithms is picking up, and people are quite interested in modeling their data. So a very interesting point which you mentioned over there about how AI is influencing design of systems. I have another question here before we close. It's about the competitive landscape, the HPC competitive landscape. How does Atos actually differentiate its integrated solutions from the other hardware providers or the other solution providers? Andy, first you, maybe QR can also jump in over there, and Michael, go ahead, please.
A key differentiation for us is around energy efficiency and use of direct liquid cooling to cool the high heat generating components such as the processors, the memory, and so on. So our systems use direct liquid cooling to cool all of those different components, and we even go as far as cooling the power supplies using water. So something like 99% or even more of the heat generated by the system is extracted by water. That makes the energy efficiency, the PUE of the platform, extremely low. You don't have to spend an awful lot of money on external cooling infrastructure because the system itself is controlling that. So we can have fairly high temperature ingress, water ingress into the system, and which means the cooling costs are very low, dependent on the geography that you're in. That's one of the key differentiators on our products. Another is the ability to offer different types of technology in a single integrated package. So as I just mentioned, the ability to have compute only, GPU only, indeed quantum components integrated into a solution. That is something that is often appreciated by customers, the ability to kind of mix and match the different components so that you can you're not trying to do a one-size-fits-all solution.
Great, very interesting about the cooling part of it over there. 90% of the heat dissipated through the water cooling system. Keyur, anything you want to add over here? Yeah, please go ahead. 99?
Yeah.
Oh, wow. Okay,
So
I got it wrong.
Yeah, there are no fans in our systems, for example. Nice. There's no requirement for mechanical cooling in the systems, and that not only makes it much more energy efficient, also reduces the noise in the platform. So our systems are extremely quiet as well, because you don't just go into a machine room and hear lots of whirring fans that you can't hear anything.
Interesting. Okay. Keyur, would you like to jump in on any points of differentiation, service differentiation of Atos in the region versus the other competitors? Go ahead.
Yes. So as Andy rightly mentioned, yes, there are definite product differentiations, but I would not like to get into the products aspect of it. From a very channel and partners perspective, what Atos typically does into HPC is a solution provider than a products provider, right? So what do we do is, customers, wanting a different HPC component, which is, let's example NetApp, for example IBM, for example DDN, right? So unlike the competition, we are able to design and tailor a solution around multiple components. We are not restricted based on a particular product. That's our key USP, especially for this region, is because customers have different preferences. Every product sits into a specific requirement. HPC is not a one knife fits all kind of a solution. So what we see are more of ourselves as a solution providers for the customers to specifically design the HPC solution based on their preferences, their choices, and the performance levels that the customer expects. We are not restricted or binded by any kind of specific product. We offer much more leeway in terms of designing our solution than the competition. So I think this is one of our at least from a solution point of view, a big takeaway, especially for the partners who are more interested to provide a consultative or a solution approach to their end users.
There's one other point I'd like to mention as well, and that's around the application support. So nobody buys a machine just to have a machine. They buy it to do work. They buy it to do applications development and develop new science. Atos has invested heavily in PhDs, in skilled resources in different application domains, whether that's in experts in weather forecasting, experts in fluid dynamics, computational engineering, and so on, life sciences. We have domain experts in each of these different areas that help construct our solutions and work with our customers to design solutions. I think that's critical. And we get involved in those large computational projects so that we keep that expertise up to date. So it's not just about selling products to customers, even if they're integrated products. It's about the whole engagement and the collaboration and the applications enablement around those products, so that we're providing customers with a tool to do a specific job, not just providing them with a tool.
Yeah, great, fantastic. And as you mentioned, Atos having a great lead in the Europe, obviously some of the leading cutting edge projects and software out of there, the extreme weather center you mentioned with 37 petaflops of performance, obviously great experience Atos has built over the region. So as we come to the close of the session, I just want to go through a round of key takeaways, some best practices, some leading thoughts which we can leave with our online channel attendees, and I guess, yes, I can see there aren't any more questions. So let's start with you, Andy. Key takeaways, anything which you want to leave the channel partners with for that think over? Go ahead.
Yeah, I mean, the key point is that we are expanding in the region and we're looking for the right kind of partners to engage with. We see a lot of potential in the region, and we think we've got a right combination of skills and technologies to really help grow the region and provide the package that business partners need to enable their engagement with their end customers. So that's the key takeaway. We can go into details on the products and services and all the other aspects, with the right kind of customer partners. But that's the key takeaway I would like to deliver. We're a leading supplier, and we want to expand in the region.
Great stuff. So Atos looking to engage with the channel partners. Great takeaway. Michael, yes, Michael, your key takeaways over there on what you would like to leave the channel audience with. Go ahead, please.
Well, apart from that, AMD has some pretty cool HPC products out there. I want the attendees to take away that our strategy is and will be that, we do support open standard programming models, and then provide our users with the best possible implementation that we can make, so that they can base their purchase decision on performance, power per performance, price per performance ratio, or whatever metric they have, and that we strive to build the best possible product according to those metrics.
Great. And of course, you mentioned about how any of the specialists can port their GPU codes, and quite a bit of the roadmaps and interportability that you have presented. Looks like AMD has got excellent structure over there. KUR, jumping to you, any key takeaways which you would like to share with the channel online attendees before we close? Go ahead.
Pretty much the same message shared by Andy and Michael on this level. I would be more than happy to get in touch with the channel partner, the channel ecosystem. The focus for us again is to not diversify and dilute and cannibalize the channel, but to focus on key partners who again have a mindset of solution and consultative approach with their end users. The plan is to go direct with channel, again to be competitive, to gain market share, and to invest and grow together with the channel in the region. So that's the bottom line.
Great stuff. So working directly with the channel partners obviously gives the partners access to the best of engineering and technology talent inside Atos. So great key takeaways, great presentations from all the speakers and all the attendees. On behalf of Global CIO Forum, Atos and AMD here, I thank all the attendees for sitting through these 675 minutes of absolutely engaging content and discussion, and look forward to seeing you once again. Goodbye and thank you.
Thank you. Thanks, everybody.
Thank you, everyone. Bye.
Thank you.